Greetings. We now have reasonable familiarity with Maxwell's equations. We know that they are the consolidation of all the empirical laws which were discovered through careful experiments performed by various scientists, whether it is Coulomb, Ohm, Kirchhoff, Oersted, Ampere, Faraday, Lenz. But then the Maxwell's equations are not just consolidation of all this under one umbrella, which that certainly is. It does two major things. One is to unify electricity and magnetism, which are not separate phenomena. And they also sort of highlight the role of symmetry in physics. Okay, the symmetry in Maxwell's equations became the foundation for many other subsequent studies in physics in which symmetry plays a very big role. So it all started with Maxwell in a certain sense, and he also used the power of mathematics in a very innovative manner and highlighted the importance of mathematics and physics going together in a seamless manner. He was not the first one to do this. The first one to do this, of course, was Newton. He, in fact, unified mathematics, physics, and astronomy. Everything came together. He invented mathematics. He invented calculus. Okay? So Maxwell was not the first one to do that, but he did it in a very big way in his time. And this is a huge contribution from James Clerk Maxwell. And we examined the Maxwell's equations, and our interest over here is to recognize that the source of the electric field are electrical charges like electrons, protons, all right? And these charges are not locked physically in space. So they are sort of, they can move around. They are mobile in that sense of the term. If you look at the second equation, which is the Faraday-Lenz-Maxwell equation, then we see that electrical fields arise not just because there is a charge, all right, which has got a certain mass and a certain charge. It has got its intrinsic properties. It has additional intrinsic properties like angular momentum and so on, which I will be soon talking about. But that's like a material particle, right? But the source of electricity can also be a time dependent magnetic field. So minus del B by del T will give you an electric field which is not irrotational. Its curl is not 0. Maxwell's equation provides room for the admission of a magnetic monopole. So you can reframe the equations with a monopole if you wish, but then no monopole has been discovered, and whatever physical magnets exist always exist as dipoles. So the divergence of the magnetic field goes to 0, unlike that of the electric charge, which is electric intensity, which is the electric charge density divided by epsilon 0, of course. And the curl of B, which is which tells us about the existence of a magnetic field, it may be due to currents, but it can also be by symmetry due to the time variation in the electric field, which is what Maxwell introduced. And these sources are what we are now going to talk about. So when you add a term like del B by del T on the right hand side of curl of E. It is not that you are changing the physics in a big way, except that you are discovering a possible additional source of the electric field. What other source in the sense another cause of the electric field. That the electric field is caused not just by material charged particles, but if you have a changing magnetic field, then also you can have an electric field. Likewise, you can have a magnetic field not just from currents, but also from time dependent electric fields. So, we have not changed anything except that we have introduced on the right hand side appropriate terms which can also cause the electromagnetic fields. And in addition to this, there may be some more causes. Okay, and those are the causes that we must now incorporate into the system. Now, regardless of what is causing this, the electric field, the nature of the electric field or the nature of the magnetic field is exactly the same, all right. So, it is not like the electric field generated by material charged particles is different from that which is generated by changing magnetic fields, and the same thing about the magnetic fields. So, you may have some additional sources which we have to take into our consideration, and that brings us to polarized dielectric materials. So, you may have a dielectric material which is polarized, which is physically neutral, but then it may have some charges. A neutral matter consists of an equal amount of negative and positive charge. So, on a macroscopic level it is neutral, but its structure involves positive and negative charges. We know that on an atomic scale you have the protons sitting in the nucleus and the electrons which are around the nucleus. These are negatively charged particles. The nucleus consists of the protons which are positively charged particles. So, if the centers of the positive and the negative charges are displaced from each other, then effectively you have a dipole, and you know that a dipole generates a magnetic moment. So, you may have a dielectric material in which there are these tiny dipoles which have come into being because the centers of the electrical positive and negative charges are not at the same point, but they are somewhat displaced from each other. So, there is a little bit of dipole moment here, another dipole moment over here, another dipole moment over here. The density of these dipole moments may not be exactly the same. Dipole moment, of course, is a vector quantity. Its orientations may also be different from different locations in the dielectric material. So, it is instructive to define what is called as a dipole moment per unit volume, and that is polarization. That is what is called as polarization. So, polarization is a vector field. It is a dipole moment per unit volume in a polarized dielectric medium, and this can be the source of additional source of electrical field. But since the nature of the electric field, whether it is generated by electric charge or a changing magnetic field or by a dipole moment inside a dielectric, all of these electric intensities are the same. They will just add up at the field point, no matter what the source is. There are similar consequences coming from magnetic dipole moments in magnetic materials, and we have to study this with a little bit of caution, and I will share this caution with you. So, magnets have been known for thousands of years, at least I would think at least 2000, and we know their properties, how other magnetic materials respond to magnets, how they orient themselves. We know about the Earth's magnetic field. So, there is a lot of empirical knowledge over hundreds of years which was available. And all of this comes together in recognizing that you have some materials, and these materials are, in some sense, you can compare them with the polarized dielectrics, because just like the polarized dielectrics have got these centers of dipole moments, okay, because the center of the plus and minus charge are not at the same point, but they are dislocated. You may have these dipole moments inside the material, magnetic dipole moments, and these dipole moments inside a magnetic material per unit volume is what you define as magnetization. So, magnetization is the net dipole moment per unit volume, and you do know, we have studied, we discussed in our previous class the multipole expansion of the vector potential, and we know that the vector potential of a dipole diminishes as 1 over r square, and it is given by this formula which you have on the screen. It is the dipole moment times the direction in which the field point is pointed, right. We know that you can add a constant vector to that if you displace the origin of the coordinate system. So, we have discussed this in our previous class, but this is the dipole moment at a field point. Okay, the dipole moment inside the magnet, it affects a magnetic vector potential at the field point, and from this magnetic vector potential the magnetic field is derivable, because the magnetic field B is the curl of the potential, del cross A is B, right. So, A at a field point is generated not just by currents, not just by changing electric fields, but also by these tiny magnetic moments or momenta which are present inside a magnetic material. So, what is the origin of this? And some older books talk about, electrons going round the protons or going round the nucleus in orbits, okay? And then they talk about a current. They interpret the charge going in these Bohr-Sommerfeld orbit as a current, and then attribute the magnetic moment generated by this motion resulting from this current, because that a current generates a magnetic field is known to us from the Biot-Savart and Ampere law. Okay? Now, this is not a very nice model, because we can use it on a tentative basis, but then later on we are going to have to abandon it, because we will have to reconcile with the fact that an orbit requires the position and momentum to be defined simultaneously. Without that, an orbit has got no meaning, right. Orbit is a trajectory in the phase space. So, that requires the position and momentum to be known simultaneously, and it turns out that measurement of one makes it impossible to get information about the other. So, you have to abandon this idea of orbit, and you can therefore no longer invoke the planetary model of the atom. And in the book by Banish Hoffman, he writes a chapter in which he writes the atom of Niels Bohr, and then his next chapter is the atom of Bohr-Niels with K-N-E-E-L-S, all right, because the planetary model really doesn't work. Okay? This is not to say that there was something wrong with Bohr's quantum mechanics. As a matter of fact, quantum mechanics has withstood the attack of a large number of brilliant minds, including Einstein, and it survived the debates basically because of Niels Bohr. So, his contribution to quantum theory is outstanding. So, there are no orbits, and you cannot really use this model. The other picture which is often used is that the electrons have got a spin, and the model of the earth rotating about its axis or a top going around its axis, it is often used to describe the electron spin, which is again not correct. Okay? And it is nothing like a spinning top or the earth going around its axis. Okay? There is absolutely no classical analog for this. These are completely new concepts. They represent intrinsic properties of particles, and these properties are intrinsic to the existence of the particle. If an electron exists, it exists along with its charge, its mass, and its spin, even if it is at rest. It does not have to go at relativistic speed, okay? But if it exists with all of these intrinsic properties. So, this was introduced on an ad hoc basis by Uhlenbeck and Goudsmit, and they use these models of a spinning top kind of thing and so on, but these models were found to be inappropriate, and these have been abandoned, and they are of course not to be used. So, now you have the electric potential which can result from a dipole moment, and you can have a magnetic moment which also results from intrinsic quantum properties of matter. Okay? So, matter or particles which make up matter like electrons, they have this intrinsic property which is called intrinsic angular momentum. It is again not to be defined as r cross p. R cross p is the classical definition of angular momentum. It does not work in quantum mechanics. So, I will discuss this when we discuss quantum mechanics in the next few classes. So, angular momentum is an intrinsic property, and associated with this angular momentum there is a corresponding proportional quantity which is the magnetic moment. So, the origin of the magnetic moment is not in this rotation of like a top, nor like the revolution around the sun in a planetary model. The origin of magnetic moment is the intrinsic angular momentum, which simply is there. If the particles are there, it is there with their charge, with their mass, and with their angular momentum. In some cases it may be 0, but it is an intrinsic property of those particles. So, the dielectric material has got these tiny weeny dipole moments spread out throughout matter, and that dipole moment per unit volume is what gives you the polarization vector. And to get the potential at a field point, all you have to do is to get the dipole potential from these different regions. Each of these tiny dipoles will generate an electric potential at this point. So, inside the bulk you will have a volume integral of the dipole moments, right. All of those have to be added up so that you get the net potential at a field point. So, this is just an additive property. All you are doing is the principle of superposition. So, now you have written this as the sum of the potentials, the dipole potentials due to different dipole momenta throughout the dielectric medium, add them up, but because we are now thinking about a continuous charge distribution, we integrate it out, and this is what we get, right. And the 1 over r square is just the gradient of 1 over r, so you can write it in this term. Now, be careful about the notation. We have got a gradient operator over there, but this is the gradient operator with respect to the primed variable, which is the source. The unprimed variable is the field point. So, you have got a field point and you have got a source point. the differentiation is with respect to the source and not with respect to the field, although you can move it around depending on what kind of algebra you are dealing with. So, here you can write the divergence of P over R. Okay. If you write the divergence of P over R, it will contain two terms, one of which is this. So, this term itself is the divergence of P over R from which you subtract the remaining term. Okay. So, we have rewritten the potential at the field point. Okay. And this one is a volume integral of the divergence. Here you use the Gauss divergence theorem and write this volume integral as a surface integral. So, you have this expression here. Now, look at these two expressions. Both have got a 1 over R structure, and this will remind you of the Coulomb's law. The Coulomb potential at a field point is just the sum of the Coulomb potentials at that point due to different charges which are spread out in a region, right. So, it is charge divided by distance, and then in SI units you have the 1 over 4 pi epsilon 0. So, 1 over 4 pi epsilon 0 charge over distance is the Coulomb potential, and you have got two terms which have got exactly the same structure, except that one of these is a charge on the surface, the other is a charge in the volume. So, you can interpret this as charge over distance and recognize the P dot n as the surface charge density, because that multiplied by the surface element ds will give you the net charge. So, this will be the surface charge density, and likewise on the second term you will have the negative divergence of the polarization as the volume charge density, because that multiplied by the volume element d tau prime will give you the net charge. So, essentially you are looking at the same type of expression as you would get from ordinary Coulomb potential. Okay. So, here you have expressed the potential at the field point as a sum of two terms, one of which is a surface integral involving the surface charge density sigma, the other is a volume charge density which is rho. And notice that I have put a subscript b on both sigma and rho. The b represents bound in the sense that these are localized charges. Okay? Unlike the free electrons in a conductor which are really mobile. So, at the slightest of application of a field, those free electrons will immediately get transported throughout the material, okay? And a voltage difference will make them actually move, and you will get a current which is J equal to sigma E, right. So, that is what you will get with mobile charges. So, these are localized charges, they are displaced for whatever reason. We are not worried at this point about what is it that has brought about this displacement. For whatever reason they are displaced, but in the structure of the matter they are going to stay where they are. They are not mobile, which is why they are called as bound charges. So, you have got the bound charge density and the volume charge density. This is coming out of the neutral matter just because of the rearrangement of the charges, and as a result of this, if you add up all the surface bound charge, it will be exactly equal to the negative of the volume bound charge. So, there is a charge conservation, the total matter is neutral. So, that is what is given in this last box over here, that the surface integral of the bound charge density is equal to the negative of the volume integral of the volume charge density rho b. So, at the beginning of today's class I mentioned that we are interpreting Maxwell's equations and expanding our understanding of what is it that generates an electric field. So, it can be charged particles, which is why the divergence of E has got rho over epsilon term. It can also be a changing magnetic field, which is why the curl of E has got the del B by del T in the Faraday Lenz law, right. Okay. And now we have to accommodate also the polarized matter, because that can also generate an electric field, and the potential at a field point can be generated because of this. Similarly, the magnetic vector potential at a field point can be generated by a magnetized material which has got the magnetic properties because of the intrinsic angular momentum, okay. And the intrinsic angular momentum can be of two different types. One is the orbital angular momentum, which has got nothing with these orbits. We have already ruled out orbits from quantum mechanics. And then we have another source of intrinsic angular momentum, which is the spin angular momentum, which has nothing to do with this rotation of a top. That is also something that we have ruled out. But we will use these terms from classical mechanics without the sense in which they were understood in pre-quantum mechanics. So, there are these additional sources of angular momentum, and therefore, they result in additional sources of magnetic moment, and this magnetic moment is the additional source of magnetism that should be incorporated in Maxwell's equations. So, the divergence of E is rho over epsilon 0. We are not tampering with that, except that we recognize that the charge density may consist of the charges that we considered earlier, charges which were free to move, which were mobile charges, and these mobile charges are what I indicate as free charges, and I write them with a subscript F. Most of this notation is from Griffith's electrodynamics, which I use extensively for this topic, right. But then it may also have an additional source, which is the bound charges. So, rho over epsilon 0 must be written as rho f plus rho b, so that you separate out the contributions of the two different types of charges. So, the Maxwell's equation has not been tampered with. So, sometimes people talk about Maxwell's equations and vacuum and Maxwell's equations and matter as if these two are different things. No, they are not. It is exactly the same thing, except that what is rho in Maxwell's equation was assumed to be only the free mobile charges, whereas now we recognize that that charge density rho, some of it may be rho f and some of it may be rho b from the bound charges in a polarized dielectric material. Okay? So, there is no change in the Maxwell's equation. The physics remains the same, the content remains the same, only that there is an explicit respect of what this dielectric, polarized dielectric can contribute to a potential there. So, that matter over here is neutral together, all right, on an average, but then outside it can have a electric potential. So, this is how Maxwell's equation gets modified. Okay, so, you now see it as being written in terms of two terms. You can now write this as divergence, negative divergence of P, because the bound charge density we know is given by negative divergence of the polarization vector. We just saw it in the previous step, right. So, now you can just rearrange these expressions and say that the free charge density is equal to the divergence of epsilon 0 E plus the polarization vector. It is just a rearrangement of terms. There is no new physics. It is just that you have recognized that rho consists of two types of charges, one which are free to move and the other which are not, which are localized, they are bound charges, right. And then you call this as the displacement field, the epsilon 0 E plus the polarization, together is the displacement field, and the first equation at the top, which is the divergence of E equal to the total charge density divided by epsilon 0, and the equation that you have at the bottom, that the divergence of D is equal to rho f. These two are completely equivalent, they are not different equations. Okay? They are exactly the same equations. There is some advantage in writing the equation at the bottom in terms of the divergence of D, because the right hand side is in terms of the free charge, and that is something that you and I can control, right. In an experiment you can control the free charge. What is locked and bound, which is due to the intrinsic properties of matter, you just have to take that matter for what it is, and that is the reason it is often advantageous to write the rho f, to write this expression in terms of rho f. And of course there are some physics becomes transparent, but you see that there is nothing new as you go from top to bottom, it is exactly the same physics. So the Maxwell's equation in matter is the same as Maxwell's equation in vacuum, except for the fact that the charge density, okay, is recognized, and it can be attributed to either the free charge or the mobile charge. You can write it in equivalent form. So you have the differential form written at the top, you can write it in the global form, in the integral form. You can take the divergence of this, and when you take the divergence of the free charge, when you integrate the free charge over the entire volume, you get the total free charge which is enclosed by that region. You can write this again using the Gauss's divergence theorem if you like, and write it in terms of a surface integral. Okay? So the polarization takes place because of the electric field. The electric field is what causes the displacement of these charges, right. And typically the polarization is proportional to the intensity of the electric field. Larger the electric intensity, larger will it separate out the positive and the negative charge centers. So you can write this expression as polarization being proportional to the electric intensity. The proportionality is in terms of the susceptibility. The susceptibility is typically, it can even have a tensor properties. It may, the electric field you apply in one direction, but the polarization may change in some other direction also. So it may have a tensor type of attribute. So when you talk about linear dielectrics, so that there is a linear relationship between polarization and the electric intensity, for them you can write D equal to epsilon 0 E plus P, and you have only defined the polarization in terms of the susceptibility. In this case, epsilon, which is 1 plus chi times epsilon 0 is the permittivity of free space. This is the dielectric constant, or the permittivity of that medium. Okay? So you have a similar situation with magnets, okay, and you have got a magnetic material which can result in a magnetic field at a field point, and you presume that this magnetic field at the field point is derivable from a potential. How would you do that? B is equal to del cross A, and the A itself, the vector potential itself, can be thought of as generated by different intrinsic magnetic momenta in the matter, which you can represent in terms of dipole moments. And then you define a dipole moment per unit volume, which is the magnetization vector capital M. So capital M is the magnetization, is the dipole magnetic moment per unit volume, and the vector potential at a field point due to this complete bulk magnet can be written in terms of the addition of the vector potential generated by these tiny dipoles spread throughout the magnet. Now, these dipoles are not like bar magnets. They have some similarity with bar magnets, but also some dissimilarity. The dissimilarity is from the fact that they are coming from intrinsic angular momenta and not from physical poles like you have in electrical dipoles. So, you do not have a south magnetic pole and a north magnetic pole, right, because individual poles with opposite signs or opposite polarity do not exist. The divergence of B is always 0 at every point anywhere in the world. So, you have this expression, and again you have got, we are doing exactly the same thing. The 1 over r gradient is 1 over r square. You have got the 1 over r square term over here, and you can write this term from the curl of m over r. So, this is the curl of this vector in the bracket, and it will consist of two terms. This is one of them. So, this term will be written as a difference of the other two terms, and this is what we have written here. Okay. So, now we have two volume integrals. One is the volume integral of this term, the second is the volume integral of this term, right. And this term is what I have written the same as here, and the term in this blue box is written as a surface integral of this term. Now, this needs a little bit of workout, which I have done on the next slide. Okay. So, I will show you how the box reduces to the corresponding term just below it. That is something that I am now going to demonstrate. So, you look at this term, the last term, which is the curl of m over r, and then you are working with a volume integral. And to do this workout, I am going to introduce two auxiliary vector fields. Then we are going to dispense with this. So, these are not fundamental to this, our discussion, but they are useful because they make it easy for us to understand the algebra. So, you have two auxiliary fields. One is Q, which is nothing but the magnetization divided by R. R is the difference distance, if you remember, between the source and the field. Okay. And then you define another auxiliary vector field, which is the cross product of the previous Q with a constant vector. What is that constant vector? It does not matter. The only thing that matters is that it is a constant vector. Okay. So, I introduce two auxiliary fields. One is m over r, which I call as Q, and the other is the cross product of Q with K, which is what I call as G. So, now I have got these two auxiliary fields, Q and G. Okay. And if you now construct this algebra, use the Gauss's divergence theorem on the divergence of Q cross R, then it is the surface integral of Q cross R dot ds, right. And we use this vector identity that the divergence of A cross B is B dot del cross A minus A dot del cross B, and using this identity we see that the volume integral of K dot del cross Q minus this volume integral of Q dot del cross K is equal to this, right, out of which this term drops out because K is a constant vector by our choice. So, its curl will vanish. So, you have got a volume integral equal to a surface integral. Now, this is about the property that we are going to use, and what we are going to further exploit is that K is a constant in this. Okay. So, K being a constant, you have the other term which is dotted with K to be equal, okay, because the dot product of two vectors will be equal when one is a constant, but an arbitrary constant. It may be oriented in any which way, It may also have a different length in any which way, right. So, the other vector must be equal. So, using this, you now have the final result over here, except that over here I had used it for unprimed variables because they did not matter, but now I am going to deal with both the primed and the unprimed variables. So, I rewrite it with primes, okay. And now I recognize that Q is nothing but m over r, which is the auxiliary field which I had used, and now I dispense with that Q. I do not need it any further, and I have this result, which is what I want to use. So, using this, I now have the final expression, okay. So, it is very straightforward, but it needs a little bit of work to do. So, you have now written the magnetic vector potential at a field point as two integrals, and look at the two terms again. They are very similar to what you get for the vector potential due to a current. This is something that we had done a couple of classes earlier, right. The vector potential at a field point is given by the volume integral of the current divided by distance, okay. So, you have got exactly the same kind of thing, and you can therefore recognize these terms in the numerator del cross m as a current, as a volume current, and m cross n also as a surface current, but these are surface current densities because they, when you multiply by dV, it becomes a current, and then you have a current over distance. There is of course a mu 0 over 4 pi constant which scales it, right. But this is not the kind of current which is resulting because of the flow of charges. This is an effective term. What is it an effect of? It is not the effect of any current at all, as a matter of fact. It has got the same form, but it is not the result of any current at all. There is no charge in flow. What is the origin of it? It is the intrinsic angular momentum and the intrinsic magnetic moment which is proportional to that. That is magnetism. There is no charge and flow, there is no current, but we are going to call it as a current because it has appeared in an equivalent expression for the vector potential. In exactly the same form as you see in this blue loop, the magnetic vector potential is given by the current divided by distance. All you have done is to superpose it. So, you have got the current density J, that multiplied by the volume element dV is the actual current, right, and the current divided by distance integrated over whole space is what gives you the vector potential. So, you have got exactly the same form, but not the same physics. Okay, there the current was like the current that was running in a wire. This is no current at all, there are no charges flowing anywhere. We are not even going to talk about the electrons going in orbits, we have dispensed with the planetary model of the atom. What we have with us are intrinsic angular momenta and intrinsic which are resulting from intrinsic angular momentum, and this is what generates the effective magnetic moment. But because it has got the same form as in the general expression for the vector potential, you call it as current. This is called as bound current because it is not really mobile, it is not transported or anything, it is just sitting there, it is coming from the intrinsic angular momentum of the matter which is sitting over there in the magnetized material. So, you have got the volume current density and the bound current density, and this is coming only from the quantum intrinsic properties. So now we had admitted in our expression for the curl of B the free current, which was the kind of current which flew in the circuits of Biot-Savart and Ampere and Oersted, right. So you have curl of B equal to mu 0 J, which was the Ampere's law or the Biot-Savart law. Then you had the contribution from del E by del T, which is the term which Maxwell put into the equation. He not only fixed the Ampere's law by using this, otherwise yesterday we discussed that there was an inconsistency. So that was resolved by this term. It also introduced symmetry in Maxwell's equations. And now we have this additional term which is coming from magnetic properties, which are coming from the intrinsic magnetic properties, which is the bound volume current density, which we know is curl of M, which we just discovered on the previous slide, right. So you can rearrange these terms so that only the free current term appears on the right, and the remaining terms you can combine and identify B over mu 0 minus M to be the magnetic intensity, as it is sometimes called. Okay. So H is B over mu 0 minus M, and you can write it in terms of if you take the surface integral of this term, you will get the free current. So that is the advantage of using H. So it allows us to write the Ampere's law in terms of the free current. So that is one big advantage, okay. But then Griffiths also warns us, which I really like in this book, that he quotes from Sommerfeld's book. It is a footnote in Griffiths' book. He says that the unhappy term magnetic field for H should be avoided as far as possible. It seems to us that this term has led into error none less than Maxwell himself. Because it's very confusing as to what is magnetic field. Is it B or H, or what is, we know that B is equal to mu H. I am going to discuss that, right. So you use a different name for B. You normally call it as a magnetic induction field or the magnetic flux field, right, and H is what you call as a magnetic field strength or the magnetic field intensity. And Griffiths recommends that he will continue to use the term field for B, and H he will simply call as H. All right, because the difference is coming from this magnetization, which is coming from an intrinsic property of matter. So don't get too much overworked by the terminology. Try to understand what is causing what. And if you remember, I discussed Ohm's law of electricity and Ohm's law of magnetism in the previous class. Both were in some sense, in the Feynman sense, can be interpreted as Newton's laws in the sense of cause effect, that the voltage difference is what results in current, okay, and likewise there is a current which results in a magnetic flux. Okay, so in that sense there is a certain similarity. So you have to use these similarities with some caution. Don't take it too far, but use them up to the point that they are useful. Okay, it doesn't mean that everything that applies to one applies also to the other. Some of the things do, some don't. So this is the magnetomotive force which I discussed in the previous class. So in both the expressions for the Ohm's law for electricity and the Ohm's law for magnetism, you have got a term R. So you have got the resistance in electricity and the reluctance in the Ohm's law for magnetism, and you have got, when alternative sources, not just the voltage difference between two terminals of a chemical battery, but you may have an alternative source which drives the current, which can be the motional EMF, where you use the Lorentz force law in which you are dragging the circuit, or where you are only changing the magnetic field over there. You have got an induced EMF, which also you call as EMF, right, although it is not a force. So, we discussed these terms quite extensively in the previous class. So, you have here the magnetomotive force, which generates the magnetic flux. And you will remember that I had introduced this magnetomotive force per unit length, because there was that integral in the integral B dot dl, there was a length element. So, you have got the magnetomotive force per unit length, and this is what H is identified with, that it is the magnetomotive force per unit length, right. So, it has got the similar kind of thing. So, if you now take just take a solenoid, for example. What happens in a solenoid? You just have a empty region of space, okay, and you have got a wire which goes around it. What does this wire do? This is the current. So, look at this as the cause effect relationship in the sense in which Feynman calls this as Newton's law, that you have got this current and it results, the cause is the current, the effect is the magnetic field which is induced inside the solenoid. Okay. So, how much of magnetic field will be induced? That depends on how much current is flowing. It also depends on how much of this length that you are considering. So, you will have to consider a property which is per unit length. So, get your mind prepared to this idea of getting a quantity per unit length. Now, instead of vacuum, if you now have a magnetic material over there, then that is going to get magnetized, right. It will have a magnetic moment per unit volume, which is capital M, and we know that B and M are not equal. The difference between them is the magnetomotive force per unit length. Okay. So, you can then, more the current that is flowing, more will be the magnetization. So, you can plot a graph between the magnetization and current, magnetization as a function of current. And when you do that, you will have this hysteresis, because when you reverse the current, okay, all the intrinsic magnetic moment which are there may not reorient themselves linearly with the applied field. Okay. They will have their own inertia, and that will result in this hysteresis loop. So, usually instead of plotting it between the magnetization and current, which is figure 6.28 in Griffith's book, what is plotted is B versus H. Okay. And in fact, another thing that I really liked about Griffith's book over here is that he plots it against mu 0 H rather than H, so that the dimensions of the two quantities are exactly the same. Okay. So, you have not just a BH curve, but a B mu H curve, mu versus mu 0 H curve. Okay. And its form will, its study will give you information about how susceptible the material is to get magnetized when you apply a field. All right. So, this is the B, it is typically called as BH curve, although it is a B comma mu 0 H curve. Okay. And I like this terminology that B is referred to as a magnetic field and H only as H, but if you wish, you can use the conventional terminology that B is the magnetic induction field or the magnetic flux field, and H as the magnetic field intensity or the magnetic field strength. Okay. So, no need to get too much overworked by this vocabulary. So, now we see that matter matters. The physics in Maxwell's equations has not changed. It is not that you have different Maxwell's equations for matter and different for different for vacuum and different for matter. It's the same Maxwell's equations, but the sources are identified as free charges or bound charges, free currents, all right, or electric field generated by changing magnetic fields and magnetic fields generated by changing electric fields, and magnetic fields or magnetic vector potentials generated by intrinsic magnetic momenta. All of these are explicitly recognized, and those terms appear on the right hand sides of these equations. And the left hand side of the equation also gets appropriately changed depending on how you write it, but the equation remains the same. Okay? So these are Maxwell's equations. Sometimes they are called as Maxwell's equations in matter. I don't personally like that term because while I recognize that matter matters, I don't want to give an impression that this is a separate family of equations. It's the same equations, but the terms are explicitly recognized. Okay? So these are the Maxwell's equations when you consider all material properties, including dielectric material and so on. And then when you bring two pieces of matter together, like in the figure that I have at the bottom, all right, a medium 1 and a medium 2, then they may have a surface of separation. And this surface of separation I also show in the figure next to it in the lower right corner of this book, that you've got a surface of separation. It may not be nice and smooth and flat, it may be warped and so on, no matter what is that surface of separation. And above the surface you have got some medium, which is medium 1, and below the surface you have got a different medium, which is medium 2. Then these properties will not be necessarily the same on the two sides of the surface, and it is important to understand how are they connected with each other. So some people call these as boundary conditions. I don't like to call them as boundary conditions, I like to call them as interface conditions, because they are really not the boundary of the whole region. The boundary is out there in the asymptotic r tending to infinity limit, all right. So these are interface conditions. So to get these interface conditions, all you have to do is to use the Gauss's divergence theorem or the Kelvin-Stokes theorem. And we know that if you apply the Gauss's divergence theorem over a Gaussian pillbox, then you can reduce a volume integral to a surface integral. And if you likewise use an Amperian loop which straddles the surface as shown in this figure, all right. So a part of this loop is above the surface, the other part is below the surface. So this is all you have to do, which is to use either the Gaussian pillbox or the Amperian loop which straddles the surface of separation, and then apply the Gauss's divergence theorem or the Kelvin-Stokes theorem. And then you can immediately see that from the volume integral of this Maxwell's equation, which is equal to the free charge density, you immediately see, because you can now cancel the A from these three terms. A is the surface area which is sitting inside that Gaussian surface element. You see that the normal components of the displacement vector are not continuous across the surface of separation, but they differ by the surface charge density. Okay? So this is the interface condition, and you can get it for other vector fields as well. You can get it for the magnetic field B, for example. If you apply the Gauss's divergence theorem for this, you can see that the normal components of B across the surface will have to be equal, because you can cancel A throughout this, right? And this gives you another interface condition for B. So they come so easily out of the Gauss's divergence theorem. Okay? So you can now use the Kelvin-Stokes theorem also. So you have got the Faraday-Lenz Maxwell relation. You take the curl, you take the line integral because of this, the surface integral of both sides will be equal, right? But the surface integral on the left hand side will be equal to the line integral through the Kelvin-Stokes theorem. Got it? So this will be equal to 0 because the surface integral of B dot ds is 0. That is nothing but the volume integral of the divergence of B, which is always 0. So what is this E dot dl? E dot dl, from the geometry you can simply see it is E1 times L minus E2 times L, where E1 and E2 are the parallel components, right? So you get this interface condition for E. And now you can do this also for H. So you have got, let us say, in this a surface current which is along a surface and the current is toward you, out of the plane of the figure. So if I represent it by an arrow, what will you see? You will see the tip of this arrow pointed toward you. Okay? So that is the direction EC over here. This is the direction of a unit vector which is directed normal to the plane of the figure and it is pointed toward you. That is the tip of the arrow. And it has got two orthogonal directions. These orthogonal directions are in the plane of the figure. One is En, the normal, and the other is Et, the E tangent. So these are the two. So now the EC, ET and En form a right-handed triad. Do you see this? So this is the geometry that we are using, and in this geometry you now have this surface current. So there is a surface of separation over here. So above this shaded area is medium 1, below the shaded area is region 2. The current is flowing on the surface toward you. So those three circles with a dot inside represent the current, the surface current which is coming toward you. And in this region I now consider an Amperian loop which is ABCDA. It is a closed loop. Q and P is where this Amperian loop intersects the surface of separation. So the loop is actually A to Q to B to C to P to D to A. That is what makes it a closed loop, right? And this integral H dot dl, you can now write, it is an integral over the closed loop. So you can write this integral over the closed loop as integral from A to Q, then from Q to B, from B to C. The integral over a line segment is the integral from this segment to a midpoint and then to another point and then to a third point and fourth point and as many as you wish, right? So that is the kind of integration that we will now carry out. So you break up the line integral over the closed path over the sum of the integrals over the path A to Q, then from Q to B, then from B to C and then from C to P, then P to D and D to A. But then remember that when you are carrying out this integration from A to Q, you are in medium 2 in the shaded region, whereas when you carry out the integration from Q to B, you are in the unshaded region, which is the region 1. Okay? So that is where the differences in the value of H will be picked. So let us do that. So this is what is done over here. So here you have got H subscripted by 2 and here you have got H subscripted by 1, because depending on where that segment is it below the surface of separation or above the surface of separation, you will be either in medium 1 or in medium 2. And some of these terms cancel. So you are left with a relatively simple relationship in which again the length segment S cancels, right, and that will give you the interface condition that the normal components, the tangential components are not equal, their difference is equal to the surface charge, surface current density. So these are the interface conditions which we have discussed in some details. I have written them in both form. On the left hand side there is a scalar form on the right hand side, there is a vector form, right? But it's essentially the same relation, there is nothing new. There are two equations which I have written, one on the left, one on the right. They are the same and they represent the difference in the displacement field given by the surface charge density. Same with the magnetic induction field, all right. This must be equal, and then you have got the interface condition for the parallel components of the electric intensity field, right, and then for the magnetic intensity field. So, I will take a break here. I will conclude today's class over here, and then in the next class we will discuss some other consequences of Maxwell's equations.